Welcome, welcome. We're really excited to be here. We have a lot to cover, so I'm not going to spend too much time saying thank you, but we do appreciate you coming here. We know there's lots and lots of sessions, so to say thank you, we'll give you a free premium trial code at the end of this presentation, which will last you 3 months. Oops, let me go back. There we go. So my name's Chris. I've been working on Grammarly's data platform for a little under 3 years now. What I'm going to do today is kind of give you a walkthrough about what is Grammarly. I'll give you a high-level architecture overview, talk about our scale a little bit. And today I have the privilege of speaking with Faraz, who is a rockstar engineer at Grammarly. He's going to do a deep dive into how do we exactly scale this data platform with limited resources. So I know a lot of people in here are really excited about LLMs, NLP, AI, and regrettably, we're not talking about that. So I did want to show you what work will look like for teams using Grammarly Business. So let's start with that with a quick 1-minute video. Super, super exciting. So again, that's kind of some of the features that we're rolling out right now, but the only thing I really wanted to speak to in terms of that slide is really the responsible AI piece. A lot of people are using other options for generative AI and all that stuff. There's been a lot of data breaches lately. Google them. Grammarly, we take a very, very user-based approach. We take care of your data. We want you to feel comfortable and safe. We don't sell data. We don't share data. We don't do any of that stuff. So you can feel nice and safe with your company's details, your company's information. It's not leaving your company. What's going on here? There we go. There we go. All right, so let's go back in time. It's 2020. November. This is about when I started at Grammarly. Like I said, like 2 and change years ago. Let's walk through like what Grammarly looked like back then. So our event rate was about 5 billion events per day. A lot of people ask me, how do you get to 5 billion even in 2022? Well, imagine you're writing a sentence. If we see a suggestion, that would be 1. We send it to you, that's 2. You view it, that's 3. You accept or decline it, that's 4. We send you another one, 5. You can see how this would bubble up with 30 million daily active users really, really quickly. The company size is about 350 employees. Why is this relevant to the data platform team? Well, all of these people are stakeholders of the data platform team. This is a very data-driven company. So all of these people in some way are interacting with the data platform team and everything that we build. Finally, we have 5 engineers owning every single component of the data platform. A lot of companies here are lean. This is very, very lean. So what do I mean when I say all aspects of the data platform? So everything in this darker gray box, the data platform team would own. So starting with ingestion, anybody that works in this space knows there's a lot that goes into that. We own everything in terms of ingestion, including even in the bottom of the second box, external integrations. This would be things like connecting to Salesforce and ad platforms and all of that stuff. If you jump up to the top of that same box, you see a lot of business logic and pipelining that we had to do. So data attribution would be users doing a bunch of activities, they sign in, and they keep doing things. We want to push that ID back in time. The data platform even owned that type of process. Moving on to storage, again, we own everything here, so indexing, cost management, access control. Any of you that have tried to do access control in a distributed file system know that that's really, really complicated. So we're also managing that. And then finally, in the last box, the analytics one, we had a custom tool called NAR, built on a lot of the same concepts of Databricks, so Spark, Parquet, AWS, a lot of things like that. But we also managed a UI. We built a custom language called GQL, which was SQL-esque. So lots of work just to keep this platform up and running. Another thing I want to call out here is that this is a very sequential pipeline. So 1, 2, 3, 4. They happen in order. On a good day, it took us about 4 hours to get from one side to the other. On a bad day, one of these things goes down. So let's imagine that attribution goes down. 5 billion events a day, that's 60,000 events per second. So in the time that I started this sentence, we already have about 600,000 events waiting to go through attribution. And that's going to take a long time for us to resolve, maybe an hour, maybe a couple of hours. Huge backlog of data all of a sudden waiting for this process. And then you can imagine what would happen downstream. So anything that finally exits that process, now we have a huge volume of data that we didn't expect. So scaling becomes an issue. Managing this pipeline becomes very, very hard. Maintenance and on-call in this system was a nightmare. Beyond that, if you think about the 350 employees, lots of asks. The data platform team's not able to roll out new features. We're not able to roll out new business logic. We're not able to drop this 4-hour latency. This number is a little bit embarrassing to us, so you can imagine that the team was very, very frustrated at this point. So this is really the world that we lived in when we started to reimagine our architecture. So let's fast forward to today. We more than doubled the team size. We're up to 13. That's great. But you can see that the company size grew about the same rate. And so all of those requests that we had in this backlog just keep building and building and building. And now with 900 plus employees, there's a ton in that backlog. Beyond that, our event rate has gone through the roof. We're now at 60 billion events per day. And you know, this is a number that's very, very difficult to comprehend. So I like to do a little example here. So let's imagine today, if you're watching online just next to you, let's imagine that for every data point, we just start stacking pennies. So for 60 billion events a day, extend that to the entire year, we're talking about 20 trillion data points. And we're just going to stack a penny up, 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 up. By the time you get to 20 trillion, you have enough pennies to get to the moon and back over 40 times. And a lot of people don't really know how far the moon is, so let's push that tower over. We're wrapping around the entire Earth 800 times. This is an incredible amount of data. And so even in one place, we consolidate it inside of Databricks. That doesn't really solve the problem of what I like to call data chaos, which is that even as a bunch of data professionals, if you come in and you're looking at 20 trillion data points, you probably have something called option paralysis, which is like, how do I get started? Even if you know where to get started, can you write effective and efficient queries on this volume of data? Probably not. So that's where data democracy comes in. What we're trying to provide here is that every function at Grammarly gets access to the data that they need, no more, no less. So by showing you less data, we help with that option paralysis. In the video, we talked about user trust and safety, and I mentioned that earlier too. This is our #1 priority as a data team. So this gives us the ability to improve our compliance, improve our security. Obviously, we're going to jump on that as well. So Lakehouse really gave us a lot. Databricks is our unified data platform. We use Okta to sync with Unity Catalog so that every user is rolled up into a role or a team. Unity Catalog then handles all of our access controls, whether that's tables, files, columns, notebooks, everything. We already spoke about our Unity Catalog implementation last year, so I can give a link to that video, but we're not going to touch on that too much. One of the understated things in this pyramid that is very, very important, however, is that middle layer, the data engineering piece. Again, we are a very small team, and we're trying to create a bunch of curated data sets. In order to do that, we have to figure out a way to streamline this process. So again, I'm throwing up this just so you can see it one more time. The only thing I want you to see here this time is, again, we had one way in, which was streaming, and we had one way out, that UI that we managed with the GQL language. And again, 4 hours to get from one side to the other. And this is our Databricks architecture now, the Lakehouse architecture. So let's talk a little bit about this. We now have 4 ways in. We can stream, we can do batch, we can do microbatch, we can do change data capture. There's one other thing in here that's not listed, which is Fivetran, which I'll talk about here in a second. And then the other thing on the opposite side, we have 8 ways out now. So SQL, Python, Scala, GQL, whatever language you want to write, you can use it. We have Tableau, we have Databricks dashboards, so you can do visualization at that BI layer. We still kept the NAR UI, so people can still use that for custom analytics. And then we have the feature store, which is for engineering platforms like experimentation and personalization, which serve data at really low latency, like sub 10 milliseconds. And the last thing I want to call out here again is at the top, the time to insights. We dropped from 4 hours to 15 minutes. A lot of this is offloading workload onto Databricks. So we no longer have to think about access control. We no longer have to think about query, visualization. This frees up this team of mine to focus on all the other components that are Grammarly-specific problems and solve data at a really, really large scale with a lean team. So I know this is pretty for a slide deck. So let's zoom in a bit. Don't let your eyes glaze over. This is what our stack actually looks like if we zoomed in a little bit. But let's talk through each of these components really, really quickly. Down at the bottom, we have Fivetran. This manages all of our external APIs. So Salesforce, ad platforms, all of that stuff. Again, it's easy to build these APIs, but we have 16 live right now. And so building and maintaining 16 API connections gets really, really tedious. Instead, we use Fivetran. They land it into Unity Catalog, and we automatically limit access based on the connector. Change data capture is a very, very similar concept. So every engineering team at Grammarly can build their own backend, their own database. We give them a process, a framework that allows them to capture all of their changes, whether that's an insert, an update, or a delete. We'll do one full copy, and then from there, just stream the changes. So it's super, super efficient. And again, we use Unity Catalog to limit access on these databases as soon as it lands based on the database owner. What you see here is where all those 60 billion events are processed. I'm not going to talk too much about this. This is a very interesting migration that we're going through of schema-less ingestion to schema-enforced ingestion. We'll talk about this in a future talk. But what I really want to call out here is the motivation. The motivation here is twofold. Data quality. If we can have schemas, we can ingest data in real time, we can serve it, we can have confidence in the quality. Beyond that, data uniformity. We want to land data in a uniform fashion so that we can use frameworks again to build all of those curated tables. It's a very framework-driven pipelining approach. So what is framework-driven pipelining? That's a great question. Again, we're a lean team. We don't want to build custom pipelines for every request, for every team. We want to create curated data sets for you so you don't have option paralysis, but we cannot do it one-off. We land about 6,000 events from this process, and so it's very, very crucial that we find an effective way of doing this. And lucky for you, that is exactly what Faraz is going to talk about. So let me call him up here to talk about how do we actually build all these curated data sets.
Hello, everyone. My name is Faraz Yasrobi. I'm a software engineer in Grammarly in the data platform team. I've been working on our data democratization project for the past couple of years, where we spent the first half year doing what just Chris talked about, and the second year we spent to build our data engineering team and extract the value out of our raw data. Let's look at this picture. This is a simple data platform where we land the raw data, and then we expose the raw data to our customers, which are people from different teams, data scientists, software engineers, data analysts, and so on. We just give them Databricks clusters they use SQL API, data frame API, and our internal tool NAR to access the data. This is the most flexible data platform that you can have because everyone can do whatever they want. But it turns out that this is not so much democracy, it's more like anarchy. People literally do whatever they want. We have a very poor performance in queries. We have a lot of duplicate pipelines. It's ridiculously expensive. And data discovery is very challenging when you're searching for things among 6,000 tables. By the way, there are two groups of raw data here. Fact tables, they're basically events, and dimension tables, which are replication of the production databases through DMS and CDC services. Now, let's clean up that previous architecture a little bit. And what we do with this is that, OK, let's add some data engineering function in between. And the role here is that, OK, they will get the raw data. Our data engineering team will also find the querying patterns, pipeline patterns, everything, and build these pipelines once, and build it right, and we will publish that data to our users. My favorite analogy here is to use the oil example. Raw data is like crude oil. It's very valuable, but it's useless as it is. It has to go through some refining process, so it becomes more valuable, it becomes gas, and we put it in our cars. Data, same thing. Raw data needs to go through some refining process to become valuable. When building data engineering teams, we have to think about two things. What tables we need to build, how do we build those tables? About the tables themselves, there are two things, structures and standards, naming conventions and things like that. And the second one is the content of the table. I'm not going to talk about the content because that's something that's derived by data science team, business intelligence team, and that kind of, like that domain. But the structure is something that we control. To solve this problem, we introduced a framework called Refine. It's just short for data refinery. This framework is supposed to be our largest scale solution to data engineering problem. This framework has two concepts, table structures and builders. So we have processing and we have storage, which we manage both. And it's supposed to work like Lego. If builders and storages are meant to be connected to each other, they will perfectly fit and they will connect. If they're not meant to connect, they will not connect. This makes the whole data engineering straightforward because we don't need to deploy and see if things work. We know them when we are developing them. Manage tables, manage processing. Why do we need to manage table? We build a lot of tables. They have to have right partitioning. There should be a lot of optimization, vacuum, documentation. There's just a lot of different features that people keep forgetting about. I've created a lot of time series tables with no time partition. There's no excuse to that. So we should have a way of protecting our users from making these kind of mistakes. So there are a lot of value to managing these things. Now, one note about Refine. It's not meant to solve all of your data engineering problems. It's just a framework to solve 80% common problems that everyone have with 20% effort. We expect all of our teams to build their own data pipelines with data frame API and so on. But the data engineering team will mostly use this framework to streamline that 80% of the work. A little bit about refined features. There are two groups of features, builder and storage. In the builder features, we do incremental processing. Within this framework, none of our developers need to invent any offset management. No one needs to keep track of what days data is complete, what days data is not complete. Everything works out of the box. The way we do this is by using structured streaming in Spark, which has an offset management system built in. The other two features in the box, which are my favorite ones, are consistent data and type safe. This system is consistent. It will handle late arriving data. So if the data comes in a little late, as long as it comes in our late arriving threshold window, we will process that. If it's out of that window, we will ignore that. And we'll have some metrics on just to check how much we are losing data. The other feature is type safety. Oh, by the way, the consistent data, the way we implement it is by using stateful structured streaming. Our pipelines memorize inputs and outputs for a short window, so when things come out of order, they know how to deal with them. The third feature is type safety. We have used Spark's dataset API and Scala case classes to build this thing end to end. So every input of the builder and output of the builder has a strict type. Same goes for the storages. Now, because of the data lineage, issues, we have probably 7-8 layers of tables until the last table that people query. So there's a long lineage. This type safety really helps us with controlling a lot of lineage issues. I'll talk about this one a little bit later. We offer backfill tools so people can deploy things faster. Also, we have a bunch of storage features. Storage features are not rocket science. It's just we should use Unity Catalog and Delta Lake's features correctly. Just make sure to have proper partitioning, proper optimization. They should be scheduled. You are not over-optimizing. You're not under-optimizing. It's just use the Databricks tools correctly. OK, now a little about those table structures. As I mentioned, we have 5 of them: fact, time series, dimension, dimension history, and dimension snapshot. Fact table is our most common table structure. They're just event tables. And the information that you find in a fact table is an event timestamp on when this event happened and some details about this event. Yeah, there's not much to it. It's just a regular event table. The point here is that we have a lot of these, 6,000 plus. And these tables have one very bad characteristic. They have unbounded volume. There's no guarantee that you will receive, in a period of 1 hour, you can receive a lot of events, and there's usually no control on it. And that makes working with fact tables very difficult. The solution to that is to introduce time series tables. You group by time window, reduce the data volume, and that's it. For example, here, the same table, now we have an overlay representation of that. It introduces inaccuracy to the data. Basically, you have one data point representing your entire window, which is not a good thing, but in general, that's OK. Most of our aggregations are hourly and daily, and it turns out that we don't lose too much. The third data type is the dimension table, and the timeless version. This table represents the latest state of every entity in the table. For example, Grammarly, one of the ways Grammarly works is you have a B2B model, so we have institutions as our customers, and there's an institution table. The row that is in the box is one of the institutions, how many provision seats this institution have, how many of them are occupied, and how many members are invited. It's just the information about the latest state of the institution. Another data structure we have is dimension history. Dimension history is not about the latest state of the entities anymore. It's about how they have changed over time. The keyword for this in the industry is SCD type 2. Basically, we observe how entities change over time. For the same entity that we had in the previous slide, there are 3 rows in this table saying that, OK, from this time to that time, the values were that, and so on. This table structure, if your data is changing slowly, it's the most efficient way to store the data. And data scientists love this because it's compact and it gives you a lot of value with almost losing nothing. Another table structure which is very popular in Grammarly is dimension snapshot. ML people love this data structure. They take for example, they take a snapshot of the dimension tables at the end of the day, and it builds this nice data set to train models. Yeah, there's not much into it, so it's just that we take the snapshot at the regular hours, at end of the day, or hourly, and it works. Now that we know about table structures, now let's see how they can be built. We use builders, refined builders, to build these different data structures. And I'm going to talk about each of them one by one with a little details. Most famous builder that I'm pretty sure everyone has in their data pipelines is fact roller. All it does is that it takes an interval of the data, groups it, and builds one data point for that. In this example at the top left, we have an input table. There are 3 data points for one day. And we do a daily grouping, so the result has 1 data point. Something that I want to emphasize is that this table structure, you will lose some inaccuracy. So it's really important to choose the time window correctly. Fact roller gives us 2 nice benefits. One of them is that it significantly reduces data volume. Chris mentioned earlier that, OK, with every interaction of the user, we are producing a data point. But in our data pipeline, we absolutely don't need all these data points. We just have to extract some value from them, do some grouping, and use downstream. The second benefit is that it gives you rate guarantee. Because of our pipeline's nature, which is stateful streaming, we need to have a rate guarantee. So to be able to keep things in memory and run this whole thing in memory end to end. The second type of table builder is the dimension builder, where we take the fact data and then build a dimension from that. For example, at the top left, you can see that we have a event table where this user has 2 data points, and the property one was 100, then user reported 50. Let's say we want to build a dimension where we know the total value of this thing over time. That's going to be our dimension builder. Our builders, under the line, you can see how this whole thing works under the hood. All of our storages are strongly typed, so we can build a data set from these storages, take that data set, run through structured streaming pipeline, and create a new data set and insert to the final storage. This whole thing happens through that configuration that you see in the middle. We take that, convert it to Spark code, and run it. Let's look at how that configuration file looks like. It's basically a Scala code block where we specify some essential information there. The first one is data model. What's the grouping model? What's our aggregation model? Where this data is going to go, that's the table config. How we do the grouping, that's the grouping logic. And how we do the aggregation, that's the aggregation logic. A developer needs to build these configurations, plug it into the builder, and the whole thing will work end to end. And last config that I missed is the late arriving threshold. We only accept late data for a certain time window because we don't want to have our pipelines memorize these forever. Here I have an example of how this actually works in production. This is a demo example. Let's assume we created the fact table and inserted some information in it. There are 3 events there, and they're all for user ID 1, and each of them are reporting property 1. And when we build a dimension table, that just sums this value over time. So as you can see, the property total for this user was 1, 2, 3, because each event incremented it by 1. What does happen if the new events come in order? This is a simple use case. The last 3 data points were for June 1, 2, 3, and we have received a new event at June 6. So as a result, we go and create a new row in our dimension table and close the previous interval. But the tricky thing happens when the data arrives out of order. Last event was at June 6. Now we have received an event at June 5. This is an out of order data arrival, which creates a lot of problems. Like the entire data consistency problem is because of this. As you can see, our dimension builder correctly handles this case. What I mean by that is that this event is trying to reduce the total value by -10. So it correctly inserts it before the last row. The value is dropped by -10. So we go from 3 to -7. It also corrects the previous value that we have and adds 1, and we go back to -6. Another builder, which is very popular in our company, is Fact Hydrator, also known as Fact Enricher. Here's the point, is that we have a dimension history table and we have a fact table. We take the information from the dimension history and we enrich the fact table with that information. For example, here in the example, the dimension history is specifying if the user is a free user or premium user for each time interval. And we have some events for that user. We join these 2 things and build the final table where we know that if the user was free or premium at the time of event. If you are doing retention analysis, funnel analysis, you're checking how your users are working with your product, you're going to need to enrich a lot of fact tables. And this should be something that build one component that does it and just keep repeating and using it. And the last builder we have is dimension joiner. As we mentioned earlier, we have a lot of data sources. We take these data sources and build dimension. Every dimension table is just explaining one aspect of the user. But we don't want to work with 20, 30 different user tables. That's not going to be efficient querying performance. What we need to do is to build these conform dimensions by joining them. And we streamline this process as well. So we develop this generic dimension joiner, and which can take any number of dimension history tables and join them and build one dimension history table. One last thing about dimensions. Under the hood, they're all built the same way. Data sets, Scala case classes, stateful Spark structured streaming job, and the output storage. Developing the builders this way is also helping us to build the builders themselves faster. I talked about data consistency a lot. This is a situation that will happen if you don't handle late arriving data. Step one, this is a hydration case, by the way. Step one, we have one event, one dimension history. We did the hydration, and we have an event with enriched feature in it, which is the user type. A new event comes in, we take it, we enrich it, and we flag it as free because that's all we knew at that time. But later, a dimension history row comes late, which tells that, okay, in January 7, the user was premium. But the problem is we previously received the record at January 8 and flagged that row as free. Now, although in reality user was premium in that time, we flagged them as free. If we didn't run this pipeline on January 7 and instead we ran it on January 8, we would get a different result. So this creates a problem that depending on when you run your pipeline, you will have different metrics. These kind of things really drive data science and business intelligence team crazy. We have a daily active user number, we have a metric for last month, and suddenly, because we recalculated something, our DAU number changes. This cannot happen. This is like a very big problem. How do we solve data inconsistency problem? You basically have two solutions. You either have to wait until all the data arrives and then do the processing. This is not good because of the long lineage that we have. It's going to take 6-7 hours until the until the users can query the data. So we couldn't go with that option. Another option is to do stateful streaming, remember things, and use them down the road. That's the option we went with. A little about Spark's stateful streaming. It's not a well-known thing for some reason, actually for two reasons. The Python support was added very recently. Most of the Spark users are Python users, and they couldn't even use this thing. The Python support was added, I think, with version 3 point something. So that's available. The other thing is it has a steep learning curve. It takes a while to understand all the concepts like the state itself, watermarking. Like these are not easy to grasp things, but once you get once you learn them, it's not that different to the regular Spark jobs. And two things that you need to specify are that how do you want to do the grouping and how do you want to aggregate the data. If you run this in the streaming mode, for every batch of the data, your grouping function will be applied to all of the data. Then data will split into groups. For each group, the aggregation function will run, and iterator of type of input will be converted to iterator of type of output. And one more thing that you need to do within your aggregation is to update the state file. So the next job has the correct state file. The way we implemented this in our system, specifically I use Dimension Builder here, is that there's a late arriving threshold, let's assume 1 day. Our dimension builder will keep track of every single input in the past 1 day and also every single output in the past 1 day. If you're thinking that are they really caching events for entire 1 day? Yes, because we used fact roller upstream, we control the data rate upstream, so we can afford to keep the data for entire day in memory. Let's assume every human on planet is our user. So at most, we're going to have 10 billion data points in 1 day. That's the maximum. And at that point, it just becomes a money problem that how fast we want to process that. The other feature that we focus on is type safety. Why this is important is because we just got tired of column not found errors. We have a long lineage. People upstream, when they make a change that's incompatible downstream, we only know this in the runtime, which means that the code needs to be built, compiled, deployed. The next downstream job should run after and fail. It takes close to 10, 12 hours until we see that we have a bad deployment. But if we can ensure this somehow in the compile time, it means that, okay, none of the actions that we did in that 12 hours need to be done. So when someone changes, for example, in this example, the property one type from int to string, our downstream job will, this code actually will not compile. So no failures in production. We will know it in the compile time. This significantly reduces the maintenance time. And my last slide, what did we learn about this whole migration in the past 2 years? You really need to streamline 80% of the scope. There's no way we can cover all the use cases by building one pipeline at a time. If we can streamline the 80% of the problem and just put 20% effort on that, then we buy a lot of time for ourselves to focus on tricky problems, and there are a lot of tricky problems in this space. Second thing, deprecating a data pipeline takes way more than building the data pipeline. You can build a data pipeline in a day, in a week, in a month, but deprecating it will take a year. Why? Because you have to take care of all the downstream jobs. We build a table, 10 teams start using that table. The only way we can deprecate that one table is either all the downstream jobs need to be deprecated, or we have to find an alternative solution. And because of the number of teams that we deal with, this becomes very difficult. So it's important to think about it very early on, that these things that we're building, how are we going to delete them? And the last thing is be ready for requirements to change. From the point that the event happens on user's device, like they do a grammar check and so on, to the point that this data point contributes to the data visualization, there are 6, 7 teams involved, and all of their requirements are changing. In my opinion, the data engineering team is kind of most flexible component here. It's the one that connects all the teams. So just deal with like the requirements are changing. It's fine. And that was my last slide. And I'm gonna give it back to Chris.